In our last section, we will be discussing the gas laws. This is section 3.6. We're going to learn how to calculate pressure, volume, temperature, and moles of a gas. We've defined pressure many times over the past few sections. Now we're going to take a look at its units. The most common unit is the atmosphere, which is abbreviated ATM. Second most common is the millimeter of mercury, abbreviated mmHg. And the third will be the kilopascal, abbreviated kPa. We also have a unit called PSI, pounds per square inch. We don't generally use that in this class, but it is a unit that you would see if you were trying to inflate a tire, either a car tire or a bike tire with air. Down at the bottom, we have a very large conversion factor. And basically, every one of these values is equal to each other. So we could say that 1 atmosphere is equal to 101,300 pascals. We could say 101.3 kilopascals equals 760 millimeters of mercury. We could say 1 ATM equals 760 millimeters of mercury, and so forth. There's always a chance when you're doing gas law problems that you might get two different pressure units, and it's very important to make sure that they are the same when we're doing the calculation, and so doing conversions beforehand is going to be important. Up at the top, I've just boxed in the three most common units and how they're equated to each other, and you'll use that when you're doing the conversions. I've got three down there for you to look at. I'll just take you through them real quickly. Basically, you're going to use dimensional analysis. So the first thing we're going to do is take our starting amount, which is 654 millimeters of mercury. You're going to go ahead and draw in your T-chart. All right, we know we want to get rid of millimeters of mercury, so we're going to place that on the bottom. And we want to find atmosphere, so we're going to put that on top. We're going to go up to our conversion factor, and you're going to see that for every 1 ATM, there's 760 millimeters of mercury. You'll put those numbers in their designated places, and then we're ready to do the math. We're going to cross out millimeters of mercury. 654 times 1 divided by 760 is going to give us 0.861 atmospheres. If we take a look at the second problem, we're going to start off with 879 millimeters of mercury. We're going to go ahead and we're going to draw our T-chart. We're going to get rid of millimeters of mercury by placing it on the denominator. We are trying to change our unit to kPa. That's going to go on top. And then I'm going to go up to my conversion factor and realize that for every 101.3 kPa, that's equivalent to 760 millimeters of mercury. I'll put those numbers in their designated places. Then I'm going to do my math after I cancel out the common unit. 879 times 101.3 divided by 760 will give me 1.16 kPa. The last problem, 15.6 atmospheres. We're going to go ahead and draw our T-chart again. This time I'm going to get rid of atmospheres. I'm going to place it on the denominator. kPa will go on the top. I'm going to run up to my conversion factor and realize for every 101.3 kPa, that's equivalent to 1 ATM. Put those numbers in their designated places, get rid of common unit, and then do the math. 15.6 times 101.3 divided by 1 is going to give us 1580 kPa. We are doing calculations again, so it's really important to watch your significant figures. In dimensional analysis, remember, we only ever look at the starting amounts, and so if there are 3 sig figs here, our answer goes to 3 sig figs. There was 3 in the second, and the answer has 3, and in the third there was also 3, and there is 3 in our answer. When performing gas laws, our temperature unit will have to be in the Kelvin scale, and most often you will find that the temperature that you are given is in Celsius. So it's going to be important for you to convert between Celsius and Kelvin. And that is simply done by adding 273.15 to the Celsius temperature. That will give you the Kelvin scale. To make it simple, we just go ahead and say add 273. And just as a note of reference, the temperature scale with absolute zero is the Kelvin scale, and in theory, temperatures cannot fall below absolute zero. Absolute zero is negative 273.15 Celsius, or 0 Kelvin. Seen below are two examples. In the first, we're going to be converting 15.6 degrees Celsius into Kelvin. So you can see all I've done is substitute the 15.6 in for the Celsius variable. We add 273 to that, and you get your answer of 288.6. Your answer does have to have proper sig figs. Remember, in addition and subtraction, our answer cannot be more precise than the least precise value in our problem. Since there are no digits to the right of the decimal point, right here, our answer will not have any digits to the right of the decimal point as well, and so really the answer is 289 Kelvin. In the next example, I've given you 234 Kelvin, so I'm going to substitute that in to where the K is in the equation, and this time you'll realize that what's going to happen is I'm going to have to subtract 273 from both sides, and what that will give you is negative 39 degrees Celsius, and that is in proper sig figs as well. There's a very important acronym that you're going to run across every once in a while in these type problems. It is STP, and STP stands for standard temperature and pressure, and those variables are 1 atm, or any of the equivalents, 760 millimeters of mercury, 101.3 kPa, and so forth, and 0 degrees Celsius, which, once again, when we're dealing with gas laws, we need to be working in the Kelvin scale, which would be 273 Kelvin. When you perform gas law equations, the first 5 gas laws that we will learn have a before and after condition. When we look at the variables, we're going to look for a 1, which stands for the initial amount, the before, and 2, which is going to stand for the final amount, which is the after. You also need to be able to recognize the variable symbols of P for pressure, V for volume, T for temperature, and N for moles, which is really synonymous to molecules. If we take a look at our equation in the middle, this is basically saying that the initial pressure over the initial moles is equal to the final pressure over the final moles. We learned in the last section called gas relationships that pressure and volume have an inverse relationship. When pressure goes up, volume goes down, and vice versa. If you take a look at the diagram, you can see that we have a large volume, and our PSI is about 3. And you can see in the next diagram that our volume has gotten smaller, and you'll notice now that the PSI is approximately 6 to 7 PSI. This type of relationship is called an inversely proportional relationship, and this will only happen when temperature and moles of the gas are held constant. We want to remember that the 2 pressure units and the 2 volume units must match. Let's take a look at the first problem here. A gas sample is 1.05 atmospheres when at 2.5 liters. What volume would it be if the pressure was changed to 0.980 atmospheres? So we're going to use the equation V1 times P1 equals V2 times P2, because the only information given to me are pressure and volume. So this is going to be my initial pressure and my initial volume. We're trying to figure out what the second volume would be, what the final volume would be, if the pressure was changed to 0.980 atmospheres. So the first thing you see here is that the pressure units are the same. And so now we're just going to plug and chug. We're going to put those numbers, which I have defined for you over here, into the equation. And when we do that, we end up doing some quick algebra, and we get 2.7 liters. Notice that this value right here only has 2 sig figs, and that's why our answer goes to 2 sig figs as well. So we're multiplying 1.05 times 2.5, and then we're dividing both sides by 0.980 in order to get your answer, and that's what you see right here. A typical graph for Boyle's law would be one that you see on the screen. We call that a hyperbola, and you can see that at various points along the line there's that inverse relationship. Notice that this is 500 looks like atmospheres of pressure, and that's probably about 8 milliliters in volume. And if we were to drop down to say 200 atmospheres of pressure, you can see that my temperature is now about, my volume is about 18 milliliters. So as the pressure is going down, the volume is going up. We also learned about the relationship between volume and temperature, and you can see here that as volume increases, temperature also increases. And this is defined as Charles' law. You've seen this diagram before, and you can see that as long as we keep the pressure and the moles constant, if we increase the temperature, we're going to increase the volume of the gas. This is known as a directly proportional relationship, and once again, pressure and moles have to be held constant. The equation that we're going to use here is V1 over T1 equals V2 over T2, and just like before, the two volume and the two temperature units must match. We also need to remember that temperature must be in the Kelvin scale. So let's take a look at an example. What is the final volume if a 10.5 liter sample of gas is changed from 25 to 50 degrees Celsius? So one of the first things I notice is that I'm in Celsius scale. I need to be in Kelvin. So I'm going to add 273 to each of those temperatures to get the Kelvin temperature. And those are going to be my T1 and my T2. And then, of course, I've been given a V1, and you are solving for V2. All of that is put right there. So to solve this, we're going to take those variables and we're going to plug them into the V1 over T1 equals V2 over T2 equation. 10.5 over 298 is equal to V2 over 323. We are then going to cross multiply, and that's going to give us 323 times 10.5 over 298 times V. And then we're going to solve for V. The answer is going to be 11.4 liters. And once again, if I go back and I look at any of the numbers in my problem, they are all 3 sig figs, and that's why my answer is going to go to 3 sig figs as well. A typical graph of the Charles law would be a straight line running through the origin, as seen in this diagram. If you take a look at the 2 points on this line, we looked at A versus B. You can see that as I go from A to B, volume is increasing, and so is the temperature. A third relationship we discussed was temperature and pressure, and you can see that as temperature decreases in this diagram, so is the pressure. This relationship is called Gay-Lussac's law. It is a directly proportional relationship between pressure and temperature when moles and volume are held constant. Notice the equation looks very similar to the one we just talked about. P1 over T1 equals P2 over T2. And as always, the two pressure units and temperature units must match, and temperature must be in Kelvin. Let's take a look at this example problem. A sample of hydrogen gas at 47 degrees Celsius exerts a pressure of 0.329 atmospheres. The gas is then heated to 77 degrees Celsius at constant volume in moles. What will the new pressure be? So we know this is our T1, and we know this is our P1, and then we know this is our T2, and we're solving for P2. And of course we need to switch over our Celsius to Kelvin, which is what we see right here. And then you are able to kind of create this little chart right here that will help you plug those numbers into the equation. So we're going to take these numbers, we're going to plug them into the equation. P1 over T1 equals P2 over T2. Once again, we're going to cross multiply and solve algebraically, and we're going to end up getting 0.360 atmospheres. Notice our answer is in 3 sig figs, and every one of these is in 3 sig figs as well. Now be careful with this. This might look like 2 sig figs, but remember we're really adding it to 273.15, so it's really 320.15. There's really 5 sig figs there, but we're going to treat them as 3 being the smallest number. This is a typical Gay-Lussac graph. Just like the Charles law graph, it's a directly proportional graph. If I pick 2 points on this straight line, you will see that as temperature increases, pressure is also increasing as well. The relationship between volume and moles can be described by Avogadro's law. You'll notice that the equation is very similar to the Gay-Lussac and the Charles law equations. So what that means is that volume and moles are directly proportional to one another as long as pressure and temperature stay constant. Remember that the two volume units or mole units must match. Let's take a look at the example. A sample with 0.15 moles of gas has a volume of 2.5 liters. What is the volume if the sample is increased to 0.55 moles? So you can see here that they've given you N1 and V1. You're going to come up with V2, and they've changed the mole amount to 0.55, so that's going to be your N2. We're going to take all that information, which is seen here, we're going to plug it into the equation, and then we're going to cross multiply and solve for V2. Our answer is going to come out to 9.2 liters. It's 2 sig figs because the least number of digits in our original numbers is 2 as well. The last of our before and after equations is the combined gas law, and you'll notice in this equation that all 4 variables are given to you. P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. Each pair of units must match, and don't forget that the temperature unit has to be in Kelvin. So nothing is held constant here. All the variables are changing. Let's take a look at an example. What is the final volume? So we know we're solving for V2. If a 15.5 liter sample, that's got to be your V1, of gas at 755 millimeters of mercury, that has to be your P1, and 298 Kelvin, that's your T1, is changed to STP. So now we know that STP is standard temperature and pressure. Standard temperature is going to be 273 Kelvin, and standard pressure is going to be 1 atm. Now, of course, you'll notice that each pair of units must match, and because my unit of pressure was in millimeters of mercury, I need to make that standard pressure of 1 atm also millimeters of mercury, and so I'm going to select 760 millimeters of mercury as the equivalent to that. And now I'm ready to solve the problem. I'm going to take all that information, I'm going to plug it into the equation, and I'm just going to use algebra to get the answer. So you can see here that all the information has been put off to the side. We're going to plug that into the equation, and we're going to do the math. Of course, we're going to cross multiply and then solve for V2. We end up getting 14.1 liters. You'll notice that 3 sig figs is the least number of digits in all of the different variables given to you initially. And so your answer should be in 3 sig figs as well. The great thing about the combined gas law equation is you can use it to formulate all of the other gas law equations that we've just talked about, from Boyle's law all the way up to Avogadro's law. If we take a look at the example at the bottom, you can see that if volume is held constant, we just pull volume out of the equation, and now we have an equation that's going to show pressure, moles, and temperature changing, and we can solve for the unknown. Let's watch what kind of equations come out of the combined gas law as we hold certain variables constant. The first one will be holding pressure and temperature constant. So if I take the P and the T out of the combined gas law, I end up with V1 over N1 equals V2 over N2, which is Avogadro's law. If I take moles, N, and temperature, T, out of the combined gas law equation, that leaves me with P1 times V1 equals P2 times V2, which is Boyle's law. And lastly, if I hold pressure, P, and moles, N, constant, that leaves me with V1 over T1 equals V2 over T2, which is the Charles law.